information that we got to so far?
I don't.
Okay. All right. Okay, then we're going to build on that info that we had about glycolysis. Aha, Alexis is joining us. Let me find the bridge. Here we go. Okay. So we had gone over glycolysis. I gave you a simpler version of the chain reaction than the one in the book. And now we're going to look at what's happening with the hydrogens. Okay, remember that hydrogen is acidic, and so if hydrogen builds up within the muscle cell, then all those enzymes in that glycolytic chain are going to slow down quite dramatically, if not stop facilitating the chemical breakdown that they're meant to be helping out. So in that case, then we would see a reduced production of ATP for muscle contraction. Okay? So if I've got less ATP, then muscle contraction has to decrease, and that's physiological fatigue, right? The inability to maintain a rate of contraction, okay? So, we covered that. So we had some hydrogens coming off in the second half of the glycolytic chain. After it's done, it's split into 2 3-carbon molecules, and we see some hydrogens given off. Now, those hydrogens can turn pyruvate into lactate, or they can be picked up by a bus system and shuttled over to aerobic metabolism. Right? So remember that ATP-PC system and glycolysis both occur within the kind of watery substance of the cell. Aerobic metabolism occurs within the mitochondria. So anything that's coming out of glycolysis that needs to be used for aerobic metabolism has to be shuttled across the cell. Right? So glycolysis then, let me do one of my really bad diagrams here. You'll have to tell me if these diagrams don't actually help, guys, because they do look rather bad. So we've got glycolysis occurring, okay? And we have hydrogens being given off. And those hydrogens, if they just hang around in the cell, are going to turn it acidic. So for glycolysis to continue really depends on, in part, on being able to donate these hydrogens to the aerobic pathway. So the bus system is a molecule called NAD or FAD. It probably would have been easier to type this, never mind. That's an F, okay? NAD and FAD act as the buses. They can pick up the hydrogen and take it across to the mitochondria, which is the little organelle that kind of looks like that when you look at it in a diagram. All right? So the other option is that pyruvate picks up hydrogen and transforms into lactate and gets dumped into the bloodstream. All right? Does that make sense? Please say yes or no.
Yep.
Remember, I can't see you guys, all right? It's not like being in class where I can look at you and you're kind of nodding. I don't know whether you understand or don't understand unless you let me know, okay?
Yeah, I'll sit here like nodding like stupid, like you can see.
I know, I'm having that trouble with all the classes. It's not just you. We're all taking a bit of time to get used to this setup. Okay, back to our spreadsheet then. All right, so we've got a couple of options to try to reduce the level of hydrogen within the cell for as long as possible. Eventually, the hydrogen is going to build up and we have to slow down, right? So if I run 100 meters as fast as I can, and instead of stopping, I keep going to 200 meters, I can't run that second 200 meters as fast as I could run the first 100 meters, right? I have to start slowing down because gradually, even with these opportunities to get rid of hydrogen, it starts to build up in the cell because we're breaking carbohydrate down faster than we can get the hydrogen removed. If you look on page 37, when you're going back over the notes and you're looking at the chapter, there's a box there that has a cool question about using glucose as an energy source. Then doesn't that mean we can just eat candy, right? So that's quite an eye-opening little piece of information for you there, I think. All right, so in System 1, we said that the training adaptations included an increase in the amount and the activity of the enzymes involved, particularly creatine kinase, and also an increase in substrate availability. So someone who trains System 1 will have more phosphocreatine available in the muscle cell than someone who doesn't. Okay? Well, when we get to glycolysis, we have a very similar picture, but we have an additional adaptation to look at as well. All right? So first, let's have a look at what happens with the enzymes. Okay? So any changes in the activity or the amount of enzymes, we've got those 10 steps, and every step has its own set of enzymes. So if I could increase the amount or increase how quickly they're working, then that would hopefully result in increased ATP availability, okay? And increased ATP availability may lead to increased performance, all right? So some of the enzymes that we're interested in, glycogen phosphorylase is the enzyme right at the top that breaks down the stored glycogen into lumps of glucose and feeds it into the system. Okay? Phosphofructokinase is an important one because that's a rate-limiting enzyme. Okay? So changes in the levels of phosphofructokinase, PFK for short, which is much easier, right, would have more impact. Uh-oh. Huh. Okay. Hi guys, are you back?
How did we tell her?
I'll send her an email real quick.
Hi.
Oh, no.
That's it. Hey, I'm back. Can you hear me?
Yeah.
Yes.
Yeah? I have absolutely no idea what happened. It just,
We were like, what?
yeah, it just went blank. Uh-oh. Come on. Oh dear, that was funny. That's a new one. We haven't had that happen yet. Okay. Where had I got to? Was I talking about phosphofructokinase, PFK?
Yes.
Okay. So PFK is a major rate-limiting enzyme in the glycolytic chain. It plays its role right before the molecule splits in two. So if there's too little PFK available, then that would slow down ATP production in the second half, because the second half of the chain is where the ATP gets produced. Lactate dehydrogenase is facilitating pyruvate picking up that hydrogen and turning into lactate. Okay. So when we look at the research on weightlifting, sprinting and endurance training, we see an increase in the levels of enzymes that are available. The adaptations that occur seem to depend on which type of exercise it is that the piece of research was looking at. And for example, I think particularly in the weight training type studies, they've seen that when you get muscle hypertrophy, so when you're doing weight training to increase the size of the muscles, there's what I think is short term, although I don't know for certain, but the PFK takes some time to catch up with that additional size, and so it's diluted for a little while. So that would suggest that you might see some lower power production for a little bit when you first see more muscle mass. There's so many variables involved in these studies, it's difficult to know which ones are playing the major roles, to be honest. So we have enzyme adaptations, and then we're going to see substrate adaptations. Remember that adaptations are typically positive. So if I stress the body, if I stress the system, it is going to adapt in a way that benefits that system and your performance. Okay? So having more available glycogen within the muscle tissue would make it easier to feed glycolysis and produce ATP, right? Remember that if I have to feed in a blood glucose, it uses ATP to move that glucose into the system. So having extra glycogen right there in the muscle cell is very beneficial. Okay? So the increase in glycogen storage in the muscle benefits anaerobic performances, but also aerobic performances because of this link between the products of glycolysis being shuttled over into the aerobic pathway, which we'll look more at, right? Don't worry, we're going to look at that. So all kinds of activities increase intramuscular glycogen. Endurance training will increase it. And it depends which type of endurance training you do. So which muscles are doing the work are the ones that adapt. So if I'm a rower, although rowers do use their legs, but if I'm a rower, we see much more adaptation of glycogen storage in the arms and the upper back than we do in the legs. If I'm a cyclist, then all the adaptation is in the legs and the butt, right? So the research looking at endurance training has no question. We always see this increase in glycogen storage. When we look at the anaerobic activities, the research just for a change is a little bit equivocal. Some of them say they see increases, some of them say they don't see a change. But again, when you tease out what kinds of activities they were looking at, then we see a pattern. So if they're doing something that is less than 10 seconds, they don't see a change in muscle glycogen because I'm not using glycolysis, right? If the activity is less than 10 seconds, which system am I using?
Anaerobic, I think less than 10 seconds.
Yeah,
Right.
the first one, right? ATP-PC, because that goes up to 30 seconds. Right? So if I'm using the ATP-PC system, why would I see an adaptation in the substrate for glycolysis? So they didn't see a change. If the activity they were doing was greater than 10 seconds, that's really where we see some difference of opinion. Some of those studies say we don't see a change. Some of them say we do see a change because the longer after 10 seconds we go, the more we're going to switch over to glycolysis. So you really have to be a critical reader of the research. You've got to be able to tease out the variables that they're really looking at. Okay? Now, different to System 1, which just has those two sets of adaptations, in System 2, in glycolysis, we've got a third lot of adaptations going on to try to help with the acidic properties of the hydrogen. Okay? So, in the UK, if it's not acidic, it's, oh gosh, I haven't been home for so long now, I forget the word. Base, is that what you call it over here? Alkaline. So the other end of the spectrum from acidic is alkaline, I think you call it base. Yes? Okay. So if releasing hydrogen is going to slow down ATP production, then a great adaptation would be, well, let's store something in the cell that can balance out the acidity of the hydrogen, right? And they call that a buffer. Okay? So we see an improved ability in the muscles that are doing the anaerobic work, right? Improved ability to buffer the increase in acid levels in the cell. Okay? So if I can buffer those hydrogens even for a short amount of time, it gives me a second, 2 seconds more power to complete the activity. And as we talked about on Monday, when we're looking at anaerobic activities, often the margin for winning or losing is very, very tiny. I don't need very much benefit to make the difference between third place and first place. Right? So skeletal muscle has buffer substances in the cell. Proteins are buffers, phosphate groups, so those inorganic phosphates can act, not the inorganic phosphate on its own, but phosphate groups can act as a buffer, and also bicarbonate. Okay, so they're the keys. Right? So endurance training and sprint type training increases the levels of these buffering molecules within the cell. Okay, so that, I don't know, it says thought to prevent acidity-associated fatigue. I think it's a bit of a stretch to say it prevents it, but it delays it, right? It gives me a little bit of extra time before I start to see a decrease in power. So one of the strategies then that sprint type athletes developed was bicarbonate loading. So as we had the creatine loading for system 1, for system 2, athletes that use system 2 predominantly will often bicarbonate load. And if you want to know, we should probably cover it later in the semester when we do chapter 15, but if you want to know more about bicarbonate loading right now, you can go to page 448, and there's a piece of info, 446 and 448. 448 has the information about the problems around bicarbonate loading, because there are some physiological paybacks to bicarbonate loading that aren't very pleasant. So, so you've got to be careful how you use it. Okay, questions on system 2? When you read the textbook goes into a lot more detail and depth on the chemistry and the really kind of abstract information about these chemical reactions and things. If you like that information and it helps you learn this, by all means read it. If you start reading it and you're like, oh my God, this is like quicksand, I have no idea what it is, go back to the lecture notes and look at the level of detail and then judge what you do and don't need to really get into in the chapter. Okay? Because there's stuff in the chapter that I read and I'm like, oh no, I don't. I'm not going anywhere near that. It's way over my head, right? Okay, so we're going to start introducing the aerobic system then and looking at the transition from anaerobic work to aerobic work, because on Friday then we will start chapter 3, which is about the aerobic pathway. Okay? So we tend to introduce the energy systems as system 1, system 2, system 3, because that's the simplest way of breaking them down. Okay? In actuality, what happens is that almost 100% of the time you have aerobic metabolism gurgling away at the bottom. For the first 30 seconds, system 1 is going to be predominant. For the next 2.5 minutes, system 2 is going to be predominant. System 1 kind of blends into system 2, which then blends into system 3 around 2.5 to 3 minutes. But essentially, most of the time, all 3 systems are, as I said, gurgling away. Just depends which one is the predominant system for that particular activity. Okay? So remember that anaerobic events are typically high intensity, very short duration. Right? If they're really short, they're going to rely on intramuscular ATP and phosphocreatine. If they're edging towards a minute or a minute and a half, like a floor routine in gymnastics, then they're going to start using glycolysis. Okay? But when they're that short, they're not going to use aerobic metabolism predominantly at all. Okay? So weightlifting, shot putting, high jumping, diving, throwing, a free throw in basketball, right, or a penalty kick in soccer, those would all be anaerobic. Okay. When we look at activities that would be aerobic, then we often call those endurance events. But they don't have to be an endurance event. So if you can, I would recommend that you get into the habit of calling it anaerobic and aerobic, because the thing is, once I hit that 3-minute mark, anything after 3 minutes is predominantly aerobic metabolism. But would I call walking for 5 minutes an endurance event? I don't think I would. I don't even think I would call walking for 10 minutes an endurance event, right? So I think that sometimes some of the confusion occurs because we use this term endurance, which in our head means a 10K, a 5K at least, you know, or a marathon, or Tour de France, or running 2 or 3 miles in the morning, right? You know, I mean, a long time, right? And so I think that sometimes gets a little bit confusing. We forget that 5 minutes has a good portion of aerobic work in there, right? So, longer duration, lower intensities. We're going to look at activities that predominantly use aerobic metabolism. All right, but as I said, it doesn't necessarily have to be an endurance event. So just kind of keep that in the back of your mind, I think. Okay, so I really like this little figure, chart, whatever you want to call it, because it gives us a guideline, right? It estimates the amount of anaerobic to aerobic work that you're doing for different timelines. And then you can take your activity and work out how long is my activity. Okay, then that's the kind of balance of aerobic to anaerobic work that I'm doing. So on the left-hand side, we've got 1 to 3 seconds. It's basically 100% anaerobic work, and there's nothing coming from the aerobic system, right? At the other end, we've got 2 hours, and there's 100% of the energy is coming from aerobic, and basically nothing is coming from anaerobic. Okay? Now, why is that idea important? Okay? Because we have a principle called specificity of training. And what that principle says is that I should make my training environment and regime as close to my competitive environment and activity as I can, right? For optimal competitive performance, I need to train that performance, right? Does that make sense?
Yeah.
Yeah? So, what that means is if I am I don't know, let's say I'm a football player, right? And we watch a football game. How long is a play in football? Not the game, but a play, typically-ish. I don't know. Is it ever more than a minute? I don't watch football, you can tell. Is it ever more than a minute, right? Nah, right? So that means that although the game of football is aerobic because it's forever long, right? The actual performance is anaerobic. Okay? So, if I've got a play that is, let's say a minute, because it's easy to look at on the chart, right? If it's a minute, then 70% of the work that I'm doing is anaerobic, and maybe 30% is aerobic. Right? That means that my training program should be 70% anaerobic and 30% aerobic. Right? Specificity of training. Specificity of training can cover all sorts of things. You could use that term in relation to the environment, right? Why do we see the basketball players practicing in the arena with the music blaring and all kinds of loud noises going on? Because that's what it's going to be like when they're playing a game. So that's actually quite a good idea, because you've got to learn to be able to concentrate under those circumstances, right? It's not physiology, but it's a similar idea in a different field, right? So, as I said, this chart is a guideline, right? It estimates this balance between the two types of ATP production, but you have to remember that one of the frustrating, although challenging and fun things about exercise physiology is every single one of us is different, right? So you might have someone at this 1 minute mark who is 80% anaerobic and only 20% aerobic, right? So part of the trick, especially if you're a strength and conditioning coach, is to pick out those individual differences so you can tweak the training program to suit that individual, not the average, right? Because if I play to the average, the performance I'm going to get is average. Okay? So these percentages are an important idea to be thinking about, right? The longer the sprint, the greater the amount of ATP that's going to come from glycolysis. So if I'm doing a 400-meter sprint, 400-meter hurdles is the killer physiological event on the planet. It's an absolute nightmare physiologically. I don't know how those coaches train athletes for that event, because it's no longer anaerobic and it isn't quite aerobic. You're kind of stuck in this no man's land of energy production. That's why they really flag at the end. It is hard, that event, right? If I do successive sprint bouts, so if I'm a soccer player, say, right, or if I'm training intervals, then, and I've got some kind of rest in between the bout or the interval, then I'm going to use the longer the longer the session goes on, the more aerobic metabolism I'm going to need to deal with the fatigue from the earlier bouts and sprints. Right? So one of the pieces of data that I think is quite interesting in the chapter, they tell us that if you're doing a 40-meter sprint, that requires 120 seconds, so 2 minutes of rest, if I want to fully resynthesize ATP and phosphocreatine before the next go. Right? So how long the rest period is depends on what I want the outcome to be. Do I want to stress the system? In that case, I need the rest period to be less than 2 minutes. Do I want equivalent performance on every single attempt? In that case, I need a long rest period. Right? So the length of the recovery period impacts the level of aerobic input to energy production in those kinds of events. Soccer's a very interesting game physiologically because where you can say football is definitely anaerobic, soccer is really interesting because their time that they're on the field is aerobic, and they very rarely, if you watch people who are either really good at soccer or possibly really bad at soccer, they're very rarely standing still, right? They're on the move all the go. Now, they're not always sprinting, right? So soccer's interesting because they're moving the whole time, that's aerobic. But they have to be able to sprint, which is ATP-PC. So I have to train two systems if I'm a soccer player. Part of fun. Okay. This topic, I mean, XPhys just in general is fascinating information, and it's not easy to get a really good handle on it and apply it to your athletes, right? and your trainees or whoever you're working with. But that's what makes it fun. Right? It's a bit of a challenge to pull all the pieces of the puzzle together. I think. Oh, and that's just, that diagram is from the textbook. I think it's from your textbook. And that's just, I think it's quite an interesting makeup. So if this was a 3-second sprint, I don't know why you'd be doing a 3-second sprint. Not quite sure what you would use that for, but 55%, let's start with our ATP. Our stored ATP produces 32% of the energy. Our stored phosphocreatine would produce 55% of the energy. Glycolysis would produce 10, and then as I said, we've got that aerobic metabolism gurgling away at the bottom there. Might produce about 3% possibly. That might be overestimated, but I'm not quite sure what would you use a 3-second sprint for? It's an odd bit of data to me. What do you use? I mean, you can't run a base in 3 seconds, can you?
It's close.
Is it? Oh, okay. Goes to show what I know. Okay, so that's all I have for you. Questions, comments, ideas, confusions, any of that stuff.
Sounds good to me.
Thanks, Molly. Okay, so remember then that we're going to start chapter 3 on Friday. What does that mean?
Pre-chapter quiz.
A pre-chapter quiz, well done. Okay, All right. So tomorrow's lab, I will be talking about aerobic intensity, and this is the information that ties into those intensity measures you're supposed to be talking about and using in your physical activity log. Okay? So that will be tomorrow morning in lab. All right?